basically recreate the conditions which are in stars, in the center of stars, in fact. So there's only one natural place in the universe that fusion energy occurs. That's in the center of stars. So that's going to bring a price to it, depending on the cost and the size and complexity of the technology that's needed to recreate those things.
And we'll talk about the details of those technologies and which parts might be expensive today and which parts might be expensive in 200 years.
Exactly. It will have a revolution in it. I'm certain of it. So about clean. So clean is, at its heart, what it does is it basically converts hydrogen into it's heavier forms of hydrogen. The most predominant one that we use on Earth, and converts it into helium and some other products, but primarily helium is the product that's left behind. So helium, safe, inert gas. In fact, that's actually what our sun is doing. It's eventually going to extinguish itself because it'll just make so much helium that it doesn't do that. So in that sense, clean, because there's no emissions of carbon or pollutants that come directly from the combustion of the fuel itself.
And safe.
Safe, yeah.
We're talking about very high temperatures.
Yeah. So this is also the counterintuitive thing. So I told you temperatures, which like 50 million degrees, or it actually tends to be more like about 100 million degrees is really what we aim for. So how can 100 million degrees be safe? And it's safe because this is so much hotter than anything on Earth, where everything on Earth is at around 300 Kelvin. It's around a few tens of degrees Celsius. And what this means is that in order to get a medium to those temperatures, you have to completely isolate it from anything to do with terrestrial environment. It can have no contact, like with anything on Earth, basically. So this means this is the technology that I just described, is it fundamentally what it does is it takes this fuel and it isolates it from any terrestrial conditions so that it has no idea it's on Earth. It's not touching any object that's at room temperature.
Including the walls of the containment.
Including the walls of the containment building or containment device, or even air or anything like this. So it's that part that makes it safe in this, and there's actually another aspect to it, but that fundamental part makes it so safe. In the mainline approach to fusion is also that it's very hot, but there's very, very few particles at any time in the thing that would be the power plant. Actually, the more correct way to do it is you say there's very few particles per unit volume. So in a cubic centimeter and a cubic meter or something like that. So we can do this. So right now although we don't think of air really as there's atoms floating around us and there's a density, because if I wave my hand, I can feel the air pushing against my face. That means we're in a fluid or a gas, which is around us. That has a particular number of atoms per cubic meter. Right. So it's about, this actually turns out to be 10 to the 25th. So this is one with 25 zeros behind it per cubic meter. So we can figure out a cubic meter is about like this, the volume of this table, like the whole volume of this table. Okay, very good. So like fusion, or it's a few of those. So fusion, like the mainstream one of fusion, like what we're working on at MIT, will have 100,000 times less particles per unit volume than that. So this is very interesting because it's extraordinarily hot, 100 million degrees, but it's very tenuous. And what matters from the engineering and safety point of view is the amount of energy which is stored per unit volume, because this tells you about the scenarios and that's what you worry about, because when those kinds of energies are released suddenly, it's like, what would be the consequences, right? So the consequences of this are essentially zero, because that's less energy content than boiling water.
Because of the low density?
Because of the low density. So if you take water is at about 100 million to a billion times more dense than this. So even though it's at much lower temperature, it's actually it has more energy content. So for this reason, one of the ways that I explain this is that if you imagine a power plant that's like powering Cambridge, Massachusetts, like if you were to, which you wouldn't do this directly, but if you went like this on it, it actually extinguishes the fusion because it gets too cold immediately. Yeah. So that's the other one. And the other part is that it does not, because it works by staying hot rather than a chain reaction, it can't run out of control. That's the other part of it. So, by the way, this is what very much distinguishes it from fission. It's not a process that can run away from you because it's basically thermally stable.
What does thermally stable mean here?
That means is that you want to run it at the optimization in temperature such that if it deviates away from that temperature, the reactivity gets lower. And the reason for this is because it's hard to keep the reactivity going. Like it's a very hard fire to keep going, basically.
Oh, so it doesn't run away from you.
It can't run away.
So how difficult is the control there to keep it at that?
It varies from concept to concept, but in generally it's fairly easy to do that. And the easiest thing, it can't physically run away from you, because the other part of it is that there's just, at any given time, there's a very, very small amount of fuel available to fuse anyway. So this means that that's always intrinsically limited to this. So even if the power consumption of the device goes up, it just kind of burns itself out immediately. Yeah.
So you are just to take another tangent on a tangent, you're the director of MIT's Plasma Science and Fusion Center.
That's right.
We'll talk about, maybe you can mention some interesting aspects of the history of the center, in the broader history of MIT, and maybe broader history of science and engineering in the history of human civilization, but also just to linger on the safety aspect.
Yeah.
You know, how do you prevent, some of the amazing reactors that you're designing? How do you prevent from destroying all of human civilization in the process? What's the safety protocols?
Fusion is interesting because it's not really directly weaponizable, because what I mean by that is that you have to work very hard to make these conditions at which you can get energy gain from fusion. This means that when we design these devices with respect to application in the energy field, is that they, while they will, because they're producing large amounts of power and they will have hot things inside of them, this means that they have a level of industrial hazard, which is very similar to like you would have like in a chemical processing plant or anything like that. And any kind of energy plant actually has these as well too. But the underlying underneath it core technology like can't be directly used in a nefarious way because of the power that's being emitted. It just basically, if you try to do those things, typically it just stops working.
So the safety concerns have to do with just regular things that like equipment malfunctioning, melting of equipment, like all this kind of stuff that has nothing to do with fusion necessarily.
Yeah, I mean, usually what we worry about is the viability, because in the end we build pretty complex